Hi guys, welcome to my channel. In this video we are going to solve a question about the reinforced concrete, and the question will be the analyze of a reinforced concrete column. And so now you can see the section is given on the screen. Let's solve the question. Before we start to solve the question, if you like these videos, if you want to see more of the videos, please subscribe and share with your friends. And if I did anything wrong and it's something that you are bothered, so please comment, and I'm going to try to make the channel better for you and for all of us. So let's solve the question. For the section of the reinforced concrete column is given, estimate the axial load capacity of the column. So what is the axial load capacity? That means that I need a pure axial load, just an axial load capacity of that. So how it's going to be calculated? For the first part, NOR, we are going to calculate the NOR, okay? For the NOR, 0.85 multiplied design strength of the concrete. What is that? 13.3. Look at here. Design strength of the concrete. And this is the design strength of the steel, okay? So 13.3 multiplied H. What is H? H is this one, the height of section, and this is the width of the section. So 800 multiplied 400 plus, I have, look at here, I have an AS prime and AS, okay? So I'm going to take the summation of both steel. So 1900 plus 1900, it's going to be plus, yeah, okay? And multiplied 365. From this equation, I'm going to obtain 5004.6 kilonewton as the axial load capacity of this cross section. Now the first part is okay, so let's solve the second part. Estimate the moment capacity when the axial load is equal to 0. Okay, so now the axial load is equal to 0. That means that it is going to be something like this, and is equal to 0. Okay, so if it's n is equal to 0, I'm going to make an assumption here, okay? Make an assumption like the beam before we did. Assume the compression steel has yield, okay? So we're going to make a check, and then we're going to determine the moment of this cross section. So let's write the equation. Total F equal to 0. Look at here, we have three forces. The compression steel, here, this is the compression steel. This is the compression concrete, and this is the tension steel. So we have three forces, and we are going to write the equation due to these forces. So, and this is going to be compression steel plus compression concrete equal to tension steel. Okay, so what is the compression steel? For compression steel, it's going to be AS prime multiplied FYD plus, for the compression concrete, it's going to be 0.85 multiplied design strength of the concrete, so FCD, okay, and multiplied B and multiplied A. And this will be equal to tension steel. What is tension steel? Steel area of tension, okay, and multiplied the design strength of the steel. So let's write the things its own place. So 0.85 multiplied 13.3, okay, multiplied 400. Now I'm writing for just the compression concrete, and multiplied 0.85. Yeah, 0.85 multiplied C. What is 0.85 multiplied C? It's actually is this one. I guess you know it from the column. A is equal to K1 multiplied C. Sorry. For this question, is the type of the concrete is C20. So K is equal to 0.85. That means, okay? You can check from the tables. So now this 0.85 multiplied C, it comes from that. So now this is going to be plus AS prime, 1900 AS, 1900s. Look at here. This is AS and plus AS prime, 1900. So 1900 multiplied 365 equal to 1900 multiplied 365. So now look at the question. Now we write an equation, but look at here, these both are the same. So when I take this one to here, it's going to be equal to 0. So that means that the compression steel has not yielded, okay? So the value of neutral axis cannot be 0. So this means that the compression steel has not yielded. We need a new C value. So let's find it. I'm going to give you a formula actually, but if you apply this formula, you're going to determine the neutral axis. So the formula is this one: the compression concrete multiplied C. C, this one is the neutral axis, plus AS prime multiplied 600 minus tension steel multiplied C, okay, minus AS prime multiplied 600 and multiplied D prime equal to 0. If you write all the data into these equations, okay, into this equation, you are going to obtain the value of C equal to 76.83 millimeter, okay. And if you remember, A was equal to K1 multiplied C, okay. So what is K1? K1 is 0.75. From here, I'm going to obtain A as equal to 65.4 millimeter. So now I got the A. So let's actually make a compatibility, and we are going to determine the yield point of the both steel, okay. So how we are going to make a compatibility? Actually, I'm going to take the shape to down. I'm going to show you, okay. So 1 second. Yeah, for example, this is here. I'm going to write the equations in that part. Yeah, for example, I'm going to make a compatibility, and the value of A is equal to 65.4. Sorry, this 4, and C is 76.83. So now I have A and C. So let's write the compatibility. For example, for this one, epsilon S prime over this length, okay, this length, if you remember from the similarity of the triangular, so epsilon S prime over this length, and epsilon Cu over this length, okay. So let's write it: epsilon S prime over this length. What is this length? C minus D prime, right? Because this is D prime, rust cover. So this is going to be 76.83 and minus 50 equal to 0.003. This is the yield point of the concrete over C 76.83. Okay, sorry. Yeah. And from here, I'm going to obtain epsilon S prime equal to 0.00104, and it is smaller than epsilon S normal, the yield strength, the yield strain of steel. What is that? It is 0.001825. So epsilon S prime is smaller than this value, so that means that the compression steel has not yielded. Okay, so now let's find for the bottom steel also. For the bottom steel, epsilon S, I'm going to show you how we are going to determine it. Epsilon S divided this length equal to epsilon SU divided this length. Okay, so epsilon S divided D, because look at here, this whole length is D, right? When I subtract from the C, when I subtract C from the D, I'm going to obtain this length, okay? I'm going to obtain this length, D minus. So I don't need to write as D, I'm going to write the the value of D. D is 750 minus C. What is C? 76.8 equal to 0.003 over C, okay? This length over this length. So yes, this value over this length. And this is going to be equal to 76.83. And from here, epsilon s equal to 0.0262. Okay? And this is greater than epsilon sy. Okay? This is epsilon sy. It is the strain of the yield point of steel. This is 0.001825. So the bottom steel is yielded. So this is the tension controlled. So before we try to find the moments, we need to find what is the stress inside the top steel. Okay, inside the top steel stress. We have to determine the stress of that. Now we have the strain. So when we multiply it with the model of elasticity of steel, we are going to obtain the stress inside the steel. So this is going to be something like that. Look at here. This is model of elasticity, and multiplied epsilon s, strain of steel. So what is that? 200,000 multiplied 0.00104. It's going to be equal to 208 megapascal. Okay, now we obtain it. So let's try to calculate the moment capacity. Okay, for the moment capacity, look at here. We have three forces, and we are going to take the moment respect to the center of gravity of this section. Okay, so center of gravity of this section. It's going to, for example, this is there. We are going to take the moment respect to the center of gravity of the section. So look at here. This normally the length between from the center of gravity to the bottom, to the bottom is 400, right? But this is the 50 as the D prime rust cover. We are going to subtract from that, and we are going to also calculate from that to that point. So let's calculate the moment capacity of section. For MR will be equal to first, for example, let's start with the compression steel. 1900 multiplied 208. It is the stress inside the steel, and multiplied 350. Okay, and plus the compression concrete 0.85 as 85. 13.3, the design stack of the concrete, multiplied 400 and multiplied 65.4. It is A, the effect of the concrete block, multiplied 400 minus 65.4 over 2. Okay. From here, I'm going to I write something less. So this is going to be also the tension steel. We forgot to write the tension steel. 1900 multiplied 365 because it has yielded. Look at here. Look at here. This is the tension steel. Okay, tension steel. Tension steel it has yielded. So I'm going to write the 365. Okay. And multiply the moment arm. It is 350 millimeter. From this equation, I'm going to obtain as the moments can be carried by this cross section as 489.5 kilonewton. When the axial load is 0. Okay. Now we also calculate the moment. So let's check the third part, what it says. Estimate the balanced load capacity. Okay, we are going to determine the balanced load capacity. in what amount of load, okay, in what amount of load this bottom steel and the concrete, they will yield at the same time, okay? In which force? We need to determine that force. So this is going to be for the third part. And for example, I'm going to write an compatibility. How I'm going to write the compatibility? Sorry, I'm gonna take again this one to here. Now, for example, it can stay here. Okay. So, how we are going to write the compatibility? For example, this is CB. Okay, this is CB. This is AB, and I'm going to write epsilon S over this length and CB. Sorry, and epsilon U, epsilon CU over this length. So it's going to be something like that. The yield point of this steel, this steel is 0.001825. Okay, so I'm going to take this one to over this length and the epsilon CU over this length. 0.001825 over 750 minus CB equal to 0.003 over CB. And now from this equation, I'm going to obtain CB equal to 466.3 millimeter. And if you remember, A equal to K1 minus C, multiplied C. K1 is here 0.85. And from this, I'm going to obtain as A equal to 396.3 millimeter. And now also I obtain A and KY, so A and CB. So this is going to be, sorry, this is going to be AB. Okay, this is AB. So let's find the axial balance force, okay? Axial balance force. How it's going to be fine? I'm going to write, and here, for example, this is NB, okay? I'm going to write in here an equation. Compression concrete plus compression steel minus tension steel and minus the balance axial force, right? So when I take this balance axial force to here, it's going to be something like that. And minus tension force. So now let's write the equations, and we are going to obtain also tension, the axial force. For the compression concrete, 0.85 multiplied 13.3 and multiplied B 400 multiplied A 396.3 and plus for the compression steel 1900 multiplied 365. Why 365? Because I assume that both of them are yielded as 0.001825. Okay, they are just on their yield points. They didn't exceed it. So and plus, so it's going to be minus. Sorry, I just confused. 1900 multiplied 365 equal to the MB, right? The axial force, it's MB. So let's write here, this both will cancel each other, and we are just going to calculate this multiplication, and we are going to obtain MB as equal to 1792.068 kilonewton. Now we obtain the MB. This is the balanced axial force. So let's check what is written for the next part. Estimate the balance moment capacity. So we're going to now calculate the moment capacity. 1 second, I'm going to delete it. Yeah, for the moment capacity, this is the fourth part, I guess. Yes, for the moment capacity, for the balance moment, it's going to be something like that. This is the compression concrete multiplied d over 2, sorry, h over 2 minus a over 2. Sorry, I'm gonna write it better. H over 2. Okay, h over 2 minus a over 2. And also plus for the compression steel. For the compression steel, is going to be something like that. Compression steel multiplied h over 2 minus d prime, because I told you that when you take the moment, you are going to take the moment with respect to the midpoint of a column. Look at here, for example, this is the compression steel. Okay, this is 50 as a rust cover, because you know that this is 50 millimeter. So I'm going to subtract this one from that, the half of the cross section. 400 minus 400 minus 50 equal to 350. Okay, so, and also plus the moment plus for the tension steel. This is going to be for the tension steel multiplied h over 2 minus d prime. So let's write it here down. It's going to be 0.85 multiplied 13.3 for the compression concrete. Now I'm reaching. And 400 multiplied 396.3 and multiplied 400 minus 396.3 over 2. Okay. And also plus for the compression steel 1900 multiplied 365 and multiplied h over 2 400 minus d prime 50 plus tension steel. What is tension steel? It's again the same, 1900 multiplied 365 and multiplied 400 minus 50. And now from here I'm going to obtain the moment as 847 kilonewton meter. Okay, this is the moment, the balance moment of this cross section. So now it's okay. So let's check for the fifth part. What's written for the fifth part? I'm going to solve the fifth part, and I'm gonna divide this question to two parts. I'm going to solve the second part for another video. So it's written that for the critical values of the limiting points, draw the moments and the actual diagrams, and for the strength envelope and the command. So let's draw it. Yeah, for the fifth part, it's going to be something like that. For the fifth part, for example, we have two axes because we are going to draw a diagram. And for example, this is the pure bending. Okay, what was the pure bending? Let's check for the pure bending. For the pure bending, what was the pure bending capacity? Oh, this wasn't. It was this one, yes. 489.5. So this is 400. This is pure bending, 489.5. And what is the pure axial load capacity of this cross section? It was 5004.6. Okay, and also we got a balance, right? We got a balance. What was the balance? 800. For example, this is 847. And due to this 847, if you remember, we got a axial force as MB. Okay, let's check what is that. Okay, this point is going to be the point that we are going to switch the way of diagram. So what is the axial force? Look at here. Axial force is 1792.067. 1762.067. 067, okay? Sorry, 68, sorry. And for this one, we are going to just got these all points, these 3 points, and this is, so this will be MN diagram, okay? So now it's going to be something like that. Let's give the notation to these points. For example, this is point C, okay? And we are going to write the comments here. Area inside is safe zone. And area outside is failure zone. So this is safe and this is failure. Point A represents the axial compression, pure compression, okay? The point B represents balanced failure. And the point C represents pure bending, just bending force, okay? Bending moment. So AB, compression, failure, and BC, tension failure, okay? Now I guess we did all the commands for this part. So now I'm going to stop the video here and I'm going to continue for the other parts for the next video.